I want to play Uber.
But you can't blame anyone, you're dead.
I'm in control.
Oh my god, honey, you're a grad student.
So you're using FFT, right? You should definitely check this one out. I don't want the all. That's good. That's actually.
We need to talk. Hey group, we need to talk about our project. Some big things I've been seeing. We need to talk after class.
No.
You know what you're about to say. You have it like you're just trying to hone up stuff.
You have like you've been transforming the data, right? No. Okay. You said you have it's like what? It's the chat logs. Let me just show you.
Find your
It's
receipt.
not FFT. It's just you do that. So yeah, we just like send it on all the zero values and yeah. To show you what I mean by saying that. So like instead of having you see these they're very interesting. So what they're just gonna be and some things if you FFT shape, it will show how accurate those are like. But it depends a lot on your just try it out instead of yeah, it just shows like proper sign. Yeah. Coming to your feature. It's like right now you just need to meet ultimately you can find features you just work on which specific domain, like very specific technical. That's I really believe that right now what domain. So our tool universe again feature. So 5%. The actually more then ultimately you have to transfer between that's the end goal is to transfer off. Yeah. So like if I give you a raw data set, you can just transfer all this is bearing
Okay.
So but like it's not one time, you just use you can these 5 features which were in the domain that you can use on whole universe in order to classify. But this is about this to cover the whole universe. How we use it? So I use FFT when I'm using for that what did you guys transform? Like if I just use what you said, like all the I just work on that. Sorry, just work on mean. What do you think about mean gets? Compress. Not all, just about.
Okay, so one gesture feature was S1.
Yeah. So like you compresses on choose a mean and then it just does nothing. So this before the body part now becomes like input to PCS. And if that has a lot of features,
So now I don't know. We just have to do our one single attribute form. Okay, that makes sense. I was like, holy shit, I have to do all this again? I had to read through so many things.
Okay. So we are done. Hold on. You cannot, people at the back, can you hear me? You can? It's not working, right? Now you can hear me, right? You can? But then how do I go there? Hello? Okay, so there is some problem. There is some problem with the mic, so I don't know how we are going to do it. But let's see, unless I get some clicker, but I don't see any clicker here. You cannot, and people in the back cannot hear me? Can I come forward then? Saying overload, I don't know what that means. What overload? Hello? There is some problem. So I cannot use the mic today, and I cannot shout loud so that you can hear. So you have to come in the front. There are a lot of empty spaces. Unless I can pull this one towards me. Anyways, let's start it. I'll start with this and then I have to move there. I don't know how it will work. So we finished grading of midterm, but I cannot post the grades yet because there is some problem. The problem is like I found a lot of answers that are similar, so I have to take some actions, and it's maybe it will take a day or two to take those actions, and then we'll give your midterms back. So the thing is, I know that there is some problem because the answers are wrong. So if we have a lot of same wrong answers, then my life becomes much more easier. Right? And then there are some funny answers. Not funny. So what you do is, I saw one student drew some matrix, right? And then that student realized that that matrix is not really needed, so he cut it. He or she cut that matrix out. Then I see 3 other papers that drew the matrix and cut it. So I don't know, when you cut it, that means it's not needed. But what do you say? I'm glad that nobody write the other person's name instead of theirs. That's good. So yeah, I'll take those actions, and then I'll release the midterm scores, and then you can also look at the papers that themselves. Now it's looking good, except for the questions that were problematic. So the thing is, let's discuss the answers. Now when I am discussing the answers, I cannot use this because I have to go there. So I don't know, if you can't hear what you will do, I don't know. None of the mics are working. So if you look at the first question is pretty simple. And this is the answer. You just multiply all the probabilities, you'll get your answer. Right? So even if you don't get the exact numbers, it's fine. You'll still get points. If you just write the equations, that's fine. That will be enough. I will post the solution. So this first one I am not discussing because it's straightforward. Now the second one was a bit. So here R2 means root 2. I got lazy. I didn't do the formatting that way. So R2 means root 2. So what you do is you just put in the values and get these. So these are fine. Now what you have to see is that look at the second and fourth, and first and third, right? You can safely ignore the last row and the last coordinate. Why? Because the first and second and the third and fourth, first and third and the second and fourth, they are clearly demarcated using the fourth one. So you don't need to look at the fourth one. Same for the third one. So if you look at the boundary, then the only point where all these 4 differ is the second one. The second one, the first one is root 2, and the second one is also root 2, and none of them are root 2, all are 0. And if you look at the third one, the first one is root 2, and the others are all 0. So you have to look at the first and second. No, not the first, sorry. The second and third. The second and third. So second and third you see is root 2 x1 and root 2 x1 x2. So it has to do with something with x1 x2. Take the larger set. Right? So it turns out that if you have root 2 x1 x2 equals 0.5, you can demarcate these 2 points. So that's how you come to root 2 by 2. Right? And x1 x2 is 1 by root 2. Now a lot of people have written that x1 x2 equals 1. That is fine too. And that should be okay too. So you have to give some arguments like this. And all these answers are in the solution manual. I think do you already have access to solution manual, to this book? No? This one I was amazed. Now this question I particularly gave to identify who are using the solution manual and who are not. So I was surprised that people wrote this entire derivation. I didn't expect that you will write this derivation. I thought that maybe you will give some qualitative arguments. And that is what I wanted. I wanted you to think and make some statement type arguments, not write equations. People wrote the entire derivation. Although I cannot penalize for that. I cannot penalize technically. But that was not the purpose of this question. You should not memorize the solution manual, or you should not take the solution manual and write it in your cheat sheet. So this one, whoever wrote the entire definition, the derivation, we gave them full points. Whoever wrote 3-4 lines explaining how the proof will work, I gave them full points as well. Right? So this should not matter whether you had access to solution manual or no. Shouldn't matter. And the problem is this one. No solution manual has the answer, so that became a problem. So now the thing is, what I saw is that word-to-word matching on A, B, and C. And a lot of answers were word-to-word matching. That I don't expect, and you'll get in trouble for that. And not in serious trouble, but a little bit of trouble. So the question was, in what application can RBMs be used? We have discussed this, movies. Right? And if you have given some other applications, that's fine too. Recommendation systems. Any type of recommendation system should work. Then, okay, so we have seen that RBMs have smaller number of hidden layers. Right? Now there was a question in class that somebody asked, that what if they have higher numbers? So we discussed the answer to that as well. So if they have higher numbers, basically they can be used for feature extraction from signals. That is one possible answer. You can have other answers. Just give me one logical one. Then we said that, okay, autoencoders, we have discussed that they are stacked RBMs. What are they used for? Simple answer, that you can get a lower dimensional representation of data. So it's similar to PCA, not exactly PCA, but similar to PCA. So that you can use the lower dimensional representation and regenerate the data. So how many of you can hear me? Because I myself am having difficulty in hearing myself. So last bench, if you cannot hear, please come forward. They're open spaces. They won't eat you, these people. And so if you can't hear, just come in the front. Then the number 5 also, I don't think you had it in your solution manual. So this is one possible answer, that what will be the dimension of the resulting eigenvectors, 100 cross 100. You can reverse it. You can have 365 cross 365 also. But you have to argue about the usefulness of that. So this is a trade-off between neglecting a sensor, reducing a sensor, versus reducing some sample points in a sensor. Right? So each has its own advantage. Typically, reducing sample points doesn't mean much. But in this context, it might mean a lot of things. For example, it might tell you seasonal variabilities. It might tell you variabilities during festivals. Right? Festivals are particular days. Right? So if you see that if one particular day has a lot of variation, maybe it's due to some festivals. Right? So all those things will work in favor of the other answer. So other answer means you just transpose it. Instead of 100 cross 100, you have 365 cross 365. Instead of number of stations, you say that number of days. I want to reduce. Instead of data matrix being 100 cos 365, it will be 365 cos 100. So those kind of things you can see. So both the answers should be fine. If you got penalized for, I have given this instruction to the TS, but if you got penalized for not giving this answer but your other answer is correct, you can rethink how to grade you. But you come and check what is your grade, and then we'll take that decision. And this one was easy, I didn't need any explanation. If you have given an explanation, very good. Which one is linearly separable? Basically what you do is you take the truth value and plot it on a 2D graph. You will see whether you can draw a line on it. So this is also is there in solution manual. So if you have answers to it, it's fine. So that's it for midterm solutions. You get your grades on, no, Tuesday we'll conduct some, we'll solve some problems, and then Wednesday you'll get the grades. So this is, the problem is not the problem, you shouldn't do this because this is academic integrity problem. You should have taken a course. Did you take a course about academic integrity? Isn't it mandatory or something? Did you? Right? So you should follow what you learned in that course. And a lot of you didn't do anything, that's good. But a lot of you did. So the thing is, remember, whenever you look at other people and copy their results or their writings, then you are thinking that that other person is more intelligent than you. So when you go to jobs, give that other person the job. And you don't take your own job. Because you are not that much intelligent than the other person. So keep that in mind. You shouldn't do that. And also the problem, another thing is that I turned the camera there, right? I was recording. It's not that I was not recording. So I know who are talking. So I have a video recording evidence. So for next time, don't do it. This time I will, you'll have a small penalty. But if you do it in final, you'll have big penalty. And it can ruin careers. So don't do this kind of things. And a lot of you didn't do anything, that's good. But a lot of you did. So let's now focus on the other stuff, good stuff, better stuff. So we finished clustering. Now we are going towards interesting things. There is just one chapter that lies between us and the things that are good, right? And we need to finish that as fast as possible. Association rule mining. We have to finish it, and then we have to discuss interesting things, which very few of it will be in exam. And I will tell you which ones will be in exam. So you won't be responsible for doing analytical things on the good things that we are going to see. But these ones you will be responsible for, right? So association rule mining is there, and you should prepare for like you prepare for exams. So let's start. Unless you have questions. Do you have questions? Okay, let's start. So we had discussed this before, right? Association rule mining. A little bit we have discussed. So this is basically creating rules from databases, right? So you have transaction type database. That's an example of association rule mining. So transaction type database, which means that you go to Walmart or Albertsons or Fry's Electronics, you will see customers buying sets of things. So these are a collection of sets. Now from this collection of sets, you want to extract certain rules. Now when you extract certain rules, what are rules? Typically association rules. So that means that you are creating, so based on observations, you are creating a relationship between items. You are seeing that items are occurring together. And from there, from the observation that certain items are occurring together, from there you want to make a relation. You want to say that, okay, let's say 3 items are occurring together. You want to come to a relation that first 2 items means the third. Or you want to come to a relation that first and third means the second. Or second and third means the first. This is one type of relation you can come into. Another type of relation that you can think of is that first and second never means fourth. That kind of relation you can also come to extract. Now when you are extracting these relations are called association rules. Right? So when you are extracting these relations, you have to keep in mind that these rules doesn't mean anything. They don't mean anything. So they don't have, or not really don't have, they may or may not have any underlying reason. They may or may not. You are only focusing on the fact that they do occur. These rules do occur. Right? So you never worry about what is the reason behind this rule. Don't worry. Just be content with the fact that these rules occur. Right? So an example is, if you worry too much on the reason, you might go into a wrong decisions. You might take wrong decisions. So for example, if you look at this database, so you are seeing that there are so bread, milk, bread, diaper, beer, eggs, all these are items that the user has bought together. So here you can make a lot of rules. You can make those example of association rules. Buying diaper means you might buy beer. Buying milk and bread means you might also get eggs and coke. Buying beer and bread means you might buy milk. Right? So these are rules. Now what are the underlying reasons? There might not be any. For example, the second rule might have some reason. Why? Because typically during breakfast you have milk, bread, and typically you get an egg, and you eat an egg. So that's a typical breakfast. Now why Coke? I have no idea. I don't know who drinks Coke during breakfast. I used to when I was a graduate student, but not now. I don't do it now. So I don't know. Yeah. So that might not be a reason. Maybe Coke is for a party or something, or maybe Coke is for the lunch. But milk, bread, and eggs, that has a reason, because it might be a popular breakfast. But what about diapers? Has an association with beer. That I cannot fathom any reason for it. But it occurs, right? That rule occurs. So don't worry about the reason. Don't worry about the reason. Just see that the rule occurs. Now, what do you get out of that rule? You can make business decisions out of that rule. You can see that, okay, I'm seeing this rule occurring all the time. So let's make money out of it. So how do you make money out of it? Basically, what you can do is you can encourage this rule. You can encourage this rule. So how do you encourage this rule? Just beside the diaper aisle, keep beers, and a stack of beer. Right? So the hope is that the person will pick diaper and will look at the beer and will pick beer also. Right? And will maintain that rule. And if that rule is maintained, what you can do is you can increase sales of beer. In order to increase sales of beer, you can have more variety diapers. Sounds absurd, but that's what the rule says. Right? So that's why you don't ponder on the reasons for these rules. You just see that these rules are there, and you can encourage these rules, you can discourage these rules, you can figure out what will be the impact of these rules. For example, let's say your diaper sales are not that much, right? So you are thinking of discontinuing diapers in your store. But now you see that there is this rule that whenever diaper sales are not much, but whenever diaper has been bought, the beer sales go up. Right? So then what you think is that, okay, if I reduce my diaper sales, then my beer sales can take a hit. So don't do that. Have at least a few diapers. Right? So those kind of rules, those kind of decisions you can take from these rules. So any rule has two parts, antecedent and consequent. So antecedent means you are trying to add some reason to it. So antecedent means that something has occurred. Given something has occurred, what is the consequent? Means what might occur next. Right? So given that somebody has bought milk and bread, the probability of that person getting eggs and coke is higher because this rule is there. So that is the start of association rule might. Now the question is, how do you mind these rules automatically? Or even theoretically, how do you mind these rules? So what you need to have is, you need to define certain terms. Right? Item set. Let's define item set. So how is item set defined? Item set is a collection of one or more items. That is an item set. Just a collection of one or more items. Then you can restrict it and call it K item set. What is K item set? K item set is an item set that contains K items. So you can say 3 item set. 3 item set example is beer, diapers, milk. That is 3 item set. Then let's define something else. We define support count, right? Sigma support count. What is it? It's the frequency of occurrence of an item set. So you have a database. You have a fixed an item set, say bread, milk, bread, diaper, and then you count how many times this item set has occurred. So that is the support. That is the support count, not support. Now what is the support? It's the fraction of transactions that contain that item set. So you just divide it by the total number of items that are there in that item set. So that becomes support. So support count divided by total number of items is support. Now what is a frequent item set? A frequent item set is an item set that has a support greater than a minimum threshold. And that minimum threshold we call min sub. Let's call it min sub. Now we define association rule. What is an association rule? So an implication expression of the from x to y, where x and y are item sets. Those are item association rule. That is an association rule. So it's an implication expression from x to y. Now, do you know what is an implication expression? Yes, it's in the word. Implication means implied. But what does it actually mean? How many of you have experience with first order logic? Not a lot. No. Although you don't really need this knowledge, but it's good to have it. So what you do is you search implication truth table. That is the best way to understand first order logic. P implies Q. This is the truth table, right? Where is it? So based on the truth values of P and Q, this is the truth values of P implies Q. So what does it mean? So if P is true, and Q is true, then P implies Q is true. If P is true, Q is false, P implies Q is false. If P is false and Q is true, P implies Q is true. Both false is true. Right? So you can figure out a Boolean expression for P implies Q. So regardless of what is P, if Q is true, P implies Q is true. Now if Q is false and P is true, P implies Q is false, and if both are false, P implies Q is still true. Although you don't need it for association rule mining, you might need it to understand certain why certain metrics are organized as they are, but you don't really need it for exams and stuff. Anyways, let's come back to evaluation. So that is association rule. Now what are rule evaluation metrics? There are two things, support and confidence. Right? So what is support? A fraction of transactions that contain both x and y. So x implies y. If we are trying to figure out the association rule, x implies y, whether that really holds or not. Right? Then the support of that rule is the fraction of transactions that contain both x and y. So basically the entire item set. Right? The fraction of transactions where the entire item set is there. And what is confidence? The confidence measures how often item sets in Y appear in transaction. Items in Y appear in transactions that contain X. Right. So X is an item set. So confidence is what? Is the so you figure out the number of transactions where X is there. Now you might have some other things also, but figure out the transactions where X is there at least. Right? And then you measure the number of times Y occurs if X is there. That gives you confidence. So this is some mathematical expression of support. Support is support count of X union Y. So you take X and Y, you make an item set using X union Y, and figure out how many number of times that item set is there, X union Y. And then you divide by the total number of items. Then what is confidence? Confidence is you have already computed the support of X union Y divided by the support of X. That is the confidence. So it shows an example. Okay, milk diaper to beer. This is our association rule. So let's see whether it has a support, good support and good confidence or not. So what we'll do, we'll make that item set milk, diaper, beer. We'll make that item set. How many times does it occur? Two times, right? Number 3 and number 4. So you notice here, there are other stuff as well. Milk, diaper, beer, bread. But we count that as a part of the support of milk, diaper, beer. So here, X is an item set, but when you count the number of times X has occurred in the database, you don't just count exact X. You count the item sets that might contain X. It might have other things. Count them as well. Right? So that's why you have the support count of 2. And you divide by 5, however many. So 2 by 5 is the support of that rule. Now what is the confidence of that rule? So you count the support of milk, diaper, beer, and you have already counted it as 2. And what is the support of milk, diaper? So milk, diaper is these two, 4, 5, and 3. So 3, 4, 5. Right? So 3 times milk and diaper has occurred together. So 2 divided by 3, 0.67. That is the confidence. Right? Now a simple way to figure out association rules is to have a threshold, right, on both support and and confidence, right? So we have already seen that we have a minimum threshold for support, min sub. Right? If an item has a support greater than min sub, we call it frequent item set. Right? So we can only focus on the frequent item sets, and then say that okay, take the item set that has most confidence, take the rule which is most confidence. We can do that and generate association rules. It's easier said than done. So before even going there, how to generate association rules, let's kind of see what does this these two terms mean, support and confidence. What does these two terms mean? So what does support mean? Support means that these three items, so x implies y, right? We are trying to figure out the support of that rule. X implies y. So what happens here is that we are saying that how many times does x union y occur in the transaction data set, right? How many times does it occur? So that doesn't say yes. Support of the rule, yes. Yeah, so it says that okay, how many times x union y has occurred. And what is the confidence saying? The confidence is saying, okay, given the number of times x has occurred in the data set, how many times has y occurred? Now, if you are thinking that there is a strong rule, x implies y, can you just work with confidence? Yes? Do you need support?
No.
So why are we defining support?
If there is a sparse vector, I mean, if there is only one instance of that, then every time confidence will be 1, right?
So that's the point. So if you have high confidence and low support, let's say you had high confidence and low support, then what does it mean? That you got an association rule that might just be by chance. Maybe somebody forgot and got beer, was not supposed to, with milk and diaper, but just got beer. Maybe he thought that it was soy sauce. Just got beer. So that's a mistake. So that type of rule will then have a low support. Right? That type of rule will have a low support. So I need rules that have high support and high confidence. So the book gives a very very controversial example of global warming. So you know that people, a lot of climate scientists have made the argument that our CO2 levels are rising. And they are rising. It's true, they're rising, and they're rising at pretty fast rate because the cars are emitting carbon dioxide. Everybody is emitting carbon dioxide. World population is increasing, and then there is a increase in global temperature. Yes, global temperature is increasing as well. Right? Now the thing is, there is a tendency to link these two, right? Carbon dioxide increases, hence global temperature is increasing. So you should reduce carbon dioxide emissions. So in Australia, they introduced this rule, right, that there will be carbon tax. But then they, I think, repealed it. I forgot whether they repealed it or not. But some to this effect they have had this. But the thing is, all these kind of conclusions are taking a data set that is very small with respect to the age of the earth. Right? So the data set that they are using is starting from 1860. And then they are looking at pre-industrial region, or pre-industrial era, and industrial era, and after that, what is happening. But the Earth didn't start at 1860, right? The Earth started long time back, a lot of years back. So now, if I look at the entire data set, this rule that carbon dioxide increases, hence temperature rises, might have a very high confidence. Right? It might have a very high confidence. Yes, it's increasing. But it might not have good support. And that is the case. It doesn't have good support. If you look at prehistoric eras, what we find, I didn't do the research. What climate scientists have found, a lot of them has found, is that carbon dioxide levels were 10 times higher than what they are now. Why? Because we didn't have plants. And since carbon dioxide level was high, it supported plant growth. So now you should make it higher, carbon dioxide. You should emit more so that there are more plants. Right? So I can make that rule that high growth of plant, so high levels of carbon dioxide implies high growth of plant, high growth rate of plants, good agriculture. So we should increase carbon dioxide levels. So let's buy more cars. I can make that, and that will have a lot of good confidence as well as support. Right? So one of the aims of this course is to highlight these things, that when you are looking at data, you need to look at data the right way. Right? You shouldn't look at data the wrong way. And if you look at the data the wrong way, it might lead to conclusions that are detrimental to humanity. So now what you can say is that by looking at this low support rule that carbon dioxide increase leads to temperature rise, you can say, oh, kill people, they are exiting carbon dioxide. Right? You are exhaling carbon dioxide. Not good. Right? So that is the problem, and that can be very lethal. Right? So now there is also another rule that you can extract from this data. The rule is that you can look at the time difference between the rise in carbon dioxide and rise in temperature. If you look at data, historical data, what you find is that rise in carbon dioxide is not an antecedent. It's actually a consequent. It's a consequent of rise in temperature. Since temperature is rising, carbon dioxide level is rising. You can make that argument if you take prehistoric era data. Right? So that is another fascinating look at data. So how do you look at data? What makes sense? So these association rules, whenever you extract association rules and you try to assign meaning to it, it becomes dangerous. It can become dangerous unless you have grounded your rules using science or some arguments, hypotheses. Right? So that's why the business people are fine. They don't make reasons. They don't need reasons. They just need money. Right? I don't need reasons to make money. I just see that there is a rule, use it, and make money. So that is fine, but don't try to assign meaning to it. If you assign meaning to it, it can lead to serious consequences. So what is the rule mining task? Okay, given a set of transactions T, the goal of association rule mining is to find all rules that have support, at least a minimum support, right, greater than threshold, and confidence greater than some threshold. That is the task. Seems very easy, just go through all the rules and figure out, right? But turns out that it is computationally prohibited. Because if you have an item set, let's say 3 item set, how many rules can you generate using 3 item sets? 2 to the power 3, Right? So already is exponential. Just from one item set, generating rules is already exponential. So from n item sets of varying sizes, how many rules can you generate? Not only exponential, it becomes combinatorial. There is even more, right? More than exponential if it's combinatorial. So you cannot just write a for loop and figure out support and confidence. You cannot do that. So that is what they are saying, that okay, it becomes 3 to the power d minus 2 to the power d plus 1 if there are 3 item sets, right? No, if there are d item sets. So for this small data set. So how do you come to that? You come to that following that. So if I want to figure out the k item sets, how many item sets are there? If there are d dimensions, d means d is the possible, is the all the set of items. D is the total number of items that you can have. How many k item sets can you get? K ranges from 1 to d minus 1. Right? So you do that summation, and that is the answer. 3 to the power d minus 2 to the power d plus 1 plus 1. So it's even more than exponential. So it's computationally prohibitive. Now you can still get some rules. Some of the rules, if you look at this, so let's just fix the item set. If we fix the item set, the support of any rule will be the same, right? If we fix the item set, can it vary for different rules? So rules obtained from the same item set, can it have a different support? Different rules obtained from the same item set? No, because support of a rule is what? Just x union y, and figure out the support of that. So x union y means anyways you are getting that item set. Right? So if you fix an item set, the support of a rule is not going to change. That is the first observation. The second observation is that if you, so here milk, diaper, beer, this is all the association rules using the same item set, right? And you see that the support is the same, there are different confidences. So this opens up a possible way towards reducing that exponential number of rules. Right? This opens up a possible way. So what is the way? What you can do is you can just analyze support and confidence separately. You can analyze support and confidence separately. So what you can do is, first you can look at support. Figure out what are the frequent item sets. And then only look at the frequent item sets and compute their confidence. So don't look for support and confidence for the entire all possible association rules. For a given item set, or no, not for given, for the entire database, transaction database, what you do is you first fix a support, figure out the frequent item sets, and only do confidence analysis on the frequent item sets. Right? That is one way to reduce computational complexity. So decoupling of support and confidence. That's what they are saying. So all the above rules are binary partitions of the same item set, and rules originating from the same item set have identical support but can have different confidence. So you can decouple support and confidence. So that is the first path towards a simplification. So what you can do is you can take a two-step approach. You can first find out a frequent item set and then generate rules from that item set. Right? Although that doesn't reduce the exponential nature, because even if you have a frequent item set, still generating rules from that item set is exponential. Right? That's what we just saw. So that doesn't reduce, that doesn't make it linear or non-linear, but or polynomial, doesn't make it polynomial, but it kind of reduces a little bit. So just figure out the frequent item set and find out the rules that have high confidence. Right? So you have two major subtasks. First is frequent item set generation. Generate all item sets whose support is greater than equal to min sum. Right? Now how many item sets can there be? Given d items, how many item sets can you generate?
Before D.
Again, it's exponential. So still it is not reducing the exponential nature. It might, it is not reducing the order of computation. It might reduce by some constant factors. Right? So yeah, so first is frequent item set generation, and then you have rule generation from those frequent item sets. And as you rightly pointed out, frequent item set generation is still exponential. It's computationally expensive. So this doesn't cut it. So this is frequent item set generation. So you can generate in this way using a graph. I mean, you don't have to use a graph. You can just think about it. So including the null set, you can have A, B, C, D. These are item sets. Then A, B, A, C, A, D. So this will be exponential. Okay? So an item can be there or may not be there. So 2 to the power, however many items are there. So if you do brute force, then what is an approach? We know it's going to be exponential, but what is an approach? So each item set is a candidate frequent item set. So this is called a lattice. So you use this data structure, lattice data structure. And then each item set in the lattice is a candidate frequent item set. Now you count the support of each candidate by scanning the database, and then only apply a minimum support. So that is the algorithm. Now complexity is very high. It's n, m, w. What is n? N is the total number of items in the database. M is the total number of item sets, and w is the width of each item, maximum width you can consider. So this is the worst case complexity. So m is still 2 to the power d, so it is exponential again. So that doesn't solve any problem. So now we have to look into frequent item set generation strategies. What strategies can we take to reduce this computation? So what we can do is we can reduce the number of candidate item sets using something called an a priori principle. What is it? We'll talk about it later. Right. So it's an effective way to eliminate some candidate item sets without counting their supports. So a priori principle. So we'll talk about that later. Or you can reduce the number of comparisons. So what you do is instead of matching each candidate item set against every transaction, we can maybe reduce it to a certain subset. Either by using some advanced data structure or by reasoning that this subset doesn't make any sense. So these are the two approaches that we'll take. So let's see these approaches one by one. So this is the a priori principle. So what is the a priori principle? So if an item set is frequent, then all of its subsets must also be frequent. That is the a priori principle. So let's think about it. Does it hold water? So it says that okay, if an item set is frequent, one particular item set is frequent, then all of its subsets must also be frequent. Or in other words, what they're saying is that there is a mathematical property. So if let's say there are two item sets x and y, and x is a subset of y, then this implies that support of x has to be greater than equal to support of y. Can you argue why? Why will that hold?
Because each time y occurs, it contains x also.
Exactly. So each time y occurs, it contains x. So support of x has to be at least support of y. If x is a subset of y, support of x has to be at least support of y. Now there can be cases where x is there, but the full y is not there. Right? So there can be cases where support of x is greater. Right? So that is the a priori principle, that if an item set is frequent, then all of its subsets must also be frequent. So now what you can do? You don't need to calculate support of x.
Include the
What-
null
what
set also.
Yes?
A subset will also include the null set.
Yes.
How can the null set be frequent if the item set is frequent?
Null set doesn't matter to you. Right? Null set is everywhere. In all item set there is null set. But it doesn't matter to you. So now, how can you use this a priori principle? So what you can say is that if you figured out that y is a very frequent item set, then don't, by computing its support, right? So by computing its support, you say that y is a very frequent item set, you found out. Then you don't need to calculate support of any of the subsets of y. You know that all of those subsets are going to be frequent item sets. So that's how you can eliminate computation of support of different item sets. You can reduce the number of support computations you do. So that's how you can use a priori principle to reduce. So support of an item set never exceeds the support of its subset. That is another way of looking at this a priori principle. So what is that other way? It says that support of an item set can never exceed the supports of its subset. So you can do it the other way around also. So you calculate the support of of a subset, right? And if you see that support is less than min sub, then all its supersets you delete. You don't need to calculate support for them. So do you understand? So let's say you calculated, you are taking a bottom-up approach and you have a small item set, and you said that the support of that item set is very low, it's less than min sub. Then you can delete all item sets that contain this as the subset, because they will definitely have less than or equal to the support of that small item set. So that means they will definitely have less support than min sub. So you don't even need to compute it. Right? So you can use this principle in two ways, in top down or bottom up. Right? So this is known as the anti-monotone property of support. This and the a priori principle. Anti-monotone property of support. So the idea has been illustrated, but do we need to go through this idea? I don't think we have already explained this idea, so we don't need to go through this again. So this is a bottom up. No, actually this is depends on what you see. Do you call it bottom up, or do you call it bottom up in the sense that bottom is bigger? So depends upon that. So let's say you start from A B C D E, right? You started counting from A B C D E. So you counted the support of all these, you counted the support of all these, and figured out, okay, this is a very frequent item set, C D E, right? And these are the subsets. So all these will be very frequent. You don't need to compute all this. So the huge chunk of this lattice is gone. Or you can do it the other way. Then you can start from null, and you see that AB's support is very low. It's less than min sub. So you just delete this entire thing, and whichever has AB as its subset, just delete this entire part of the lattice. So this can significantly reduce your computation, frequent item set computation. So it gives another illustration, let's not go through the exact details of the illustration, but let's look at the results. So the results are saying that if every subset is considered, if you look at this, if every subset is considered, then you have to do 41 computations, 41 support computations, as opposed to just 13. Right? If you have min support of 3, and that is it, and you are figuring out different item sets. Right? So instead of 41, you do 13. That's a huge drop. So what is the algorithm? Now you have seen that there are two ways you can apply the a priori principle. Right? So let's see this algorithm, a priori algorithm. So let k equals 1, okay. Generate frequent item sets of length 1. So how do you generate frequent item sets of length 1? Look at all the item sets, calculate the support. Right? And then you apply the threshold. Say that okay, min sub. You keep the threshold. Now repeat until no new frequent item sets are identified. So now you are entering a loop. Right? So generate length k plus 1 candidate item sets from length k frequent item sets. So from the frequent items, only look at the frequent item sets, and you generate the length k plus 1 candidate item sets from the k frequent item sets. Then count the supports of each candidate by scanning the database. Eliminate candidates that are infrequent, leaving only those that are frequent, and then you will repeat. So the algorithm is very simple, right? Extremely simple algorithm to generate frequent item sets. Do you understand the algorithm? So they are saying that okay, you have a let's say you have at any point in the algorithm you have a set of k frequent you have a set of frequent k item sets. Then what do? You take another item and generate a k plus 1 item set from those frequent ones. Right? So you have a set of k plus 1 item sets. You calculate the support of these k plus 1s. Now you apply the threshold. Now whatever threshold you get, if certain item set doesn't meet the threshold, delete it. Now you have a k plus 1, a set of k plus 1 item set that are frequent. Continue from there. So the algorithm makes a single pass over the data to determine the support of each item. Right? So upon completion of this set, the set of all frequent 1 items will be known. And then next the algorithm iteratively generates new k items using frequent k minus 1s. So now this is just explaining what is the algorithm. We have already talked about it. So it goes now into its examples. So let's stop here today. Let's stop here and we'll talk about examples next class. Now, do you have any questions regarding assignment? Assignment was due or it's still due? Still due. Any questions about assignment? So everything is clear? That's good. Oh, I posted sample reports. So please look at those sample reports because those are indicative. So where do you go for sample reports? Go to assignment folder. There is a sample report bad and there is a sample report good. Right? So follow the good one, don't follow the bad one. Now look at the bad one to understand what went wrong. We can go today.